resistive forces between a solid object and a fluid. In this simulation, a parachute is falling downward is subjected to a resistive force from the air. In the second simulation, a swimmer is subjected to a resistive force from the water while swimming. The resistive force exerted on a solid object by a fluid, gas or liquid in which it is moving is called the fluid resistance or drag force. For an object moving in air, as in the first simulation, drag force is called air resistance.
Returning to the first simulation, the velocity of the parachutist is directed vertically downward, while the drag force or the resistive force is directed vertically upward. In the second simulation, the velocity of the swimmer is directed horizontally to the right, while the drag force directed horizontally to the left. Drag force acts in the opposite direction to the object's velocity. The work done by the drag force results in converting kinetic energy into thermal energy.
Magnitude of the drag force. We consider two cases. For small objects moving slowly in fluids, like a falling paper airplane, a falling oil drop in water, or a dusty particle in air, the main resistive force is the friction drag, which can be expressed as F equals B times V, where B is a positive constant and V is the speed of the object. For large objects moving with high speeds, like skydivers, airplanes, and cars, the main resistive force is the pressure drag, whose magnitude can be expressed as F equals B prime times V squared, where B prime is a positive constant. The positive constants depend on the surface area and shape of the object, as well as on the properties of the fluid.
Now let's study friction forces acting on rolling objects. In this video, we study the ideal case where both the rolling body and the surface on which it rolls are perfectly rigid. Let's start by studying the motion of a ball on a frictionless inclined plane. A ball is placed at the top of a frictionless inclined plane. When it is released, it slides without rotation and attains a speed of 3 meters per second at the bottom of the incline.
Why does the ball slide down with no rotation? The external forces acting on the ball during its motion are its weight and the normal force. Since both the weight and the normal force pass through the center of mass of the ball, neither force has a rotational effect about the center of mass. Therefore, the ball slides down with no rotation.
In a simulation similar to the previous one, a ball is placed at the top of a rough inclined plane with sufficient friction. Let's observe the effect of the friction on the motion of the ball. When the ball is released, it rolls down the incline with no slipping and attains a speed of 2.6 meters per second at the bottom of the incline.
Why does the ball rotate as it moves down the incline? Since the contact points of the ball tend to slide down, the ball is subjected to an upward frictional force in addition to its weight and the normal force. This frictional force creates a torque about the ball's center of mass, causing it to rotate.
The frictional force is opposite to the velocity of the center of mass and creates a torque about the ball's center of mass. Then, the frictional force resists the translational motion and aids in the rotational motion of the ball. Therefore, this slide disproves the first misconception and shows that the frictional force can induce the rotational motion of a rolling object.
Despite the presence of friction, is the mechanical energy of the ball-earth system conserved? The contact points between the ball and the inclined surface are momentarily at rest, so the frictional force does no work. We can also prove that, during the motion of the ball, The decrease in translational kinetic energy equals the increase in rotational kinetic energy. Therefore, the mechanical energy of the system is conserved. This slide disproves the second misconception and shows that friction does not always cause a decrease in mechanical energy or produce thermal energy.
In rolling motion, when the contact points tend to move forwards, the frictional force resists the translational motion and aids in the rotational motion. Examples include a ball rolling down a frictional inclined plane, a rolling wheel of a wheelbarrow, a rolling wheel of a horse-drawn carriage.
Is friction necessary for a car to move? Consider this short video. Initially, the vehicle is at rest on a muddy, frictionless surface. When the driver attempts to move the vehicle, the rear wheels spin without any translational motion.
Why do the rear wheels and thus the car have no translational motion on a muddy surface? When the vehicle is at rest, each wheel is subjected to two equal and opposite vertical forces. As the engine rotates the rear wheels, no friction force acts between the contact points of the wheels and the road. Therefore, the net force on each wheel is zero and the wheels and thus the car have no translational motion.
Now the vehicle is initially at rest on a surface with sufficient friction. When the driver attempts to move the vehicle, the wheel rolls undergoing both translational and rotational motion.
Why does the wheel undergo rotational and translational motion? Initially, the engine rotates the wheel in the anti-clockwise direction. The contact points tend to slide backwards. The wheel is subjected to a forward frictional force. This makes the wheel moving forward.
The frictional force is a forward traction force directed in the same direction as the vehicle's velocity. Additionally, it creates a negative torque about the wheel center of mass. So we can conclude that the frictional force aids in the translational motion and resists the rotational motion of the wheel. Therefore, this slide disproves the third misconception and shows that the frictional force can induce the translational motion of a rolling object.
Despite the presence of friction, is the mechanical energy of the vehicle Earth system conserved? Similar to the rolling ball on a rough inclined plane, the contact points between the wheels and the ground are momentarily at rest, so the frictional force does no work. We can also prove that during the motion of the vehicle, the decrease in rotational kinetic energy equals the increase in translational kinetic energy. Therefore, the mechanical energy of the system is conserved.
In rolling motion, when the contact points tend to move backward, the frictional force resists the rotational motion and aids in the translational motion. Examples include a rolling vehicle wheel on a frictional surface, a rolling bicycle wheel,